So can you talk about the different areas or categories of artificial intelligence?
Now, there are lots of different fields that AI works in, but if I were to, on a very, very high level, group some of the major areas where artificial intelligence is applied, I'd like to start off with natural language. Because natural language is, I'd say, the most complex data for machine learning to work with. If you see all sorts of data, whether that be a sequenced genome, whether that be audio, whether that be images, there's some sort of discernible pattern. There's some sort of, yes, this is what a car sounds like, or yes, this is what human voice sounds like. But natural language is fundamentally a very human task. It's a very human data source. We as humans invented it for humans to understand. If I were to, for example, give you a book title, there's actually a very, very famous book, and the title of the book is "There Are Two Mistakes in the title of this book." Now, there's actually only one mistake. There are two thes. The human brain doesn't realize that. What's the second mistake? That there was only one mistake. So this is the sort of natural language complexity that's involved here. Humans don't view natural language literally. We view it conceptually. If I were to write a 3 instead of an E, you would understand it because we don't mean the 3 in a literal sense. We mean that in a symbolic sense to represent the concept of E. And you can contextualize that 3 to figure out that, yeah, it means an E and not an actual 3. These are things that computers aren't capable of. So natural language is the number one sort of field that I'm most interested in when it comes to machine learning. Second, I'd say the most popular would be visual data understanding, computer vision, because it enables us to do so many things. I mean, as humans, our primary sense is vision. In fact, a vast majority of your brain's processing power at any given moment goes to understanding what it is that you're seeing, whether it be a person's face, or whether it be a computer, or some text, or anything of that sort. And third, I would say audio-based data. So text-to-speech, speech-to-text, these are very, very complex. And the reason it's complex is because it kind of combines a lot of challenges into one. First of all, you've got to support many languages. You can't just support English and call it a day. You've got to support the other languages. You've got to support other demographics. And another challenge is that even within languages, there are absolutely infinite number of ways that any human could represent a language. Everyone's going to have a different accent. Everyone's going to have a different way of pronouncing certain words. There's no standardized way that every human will pronounce ice cube exactly like ice cube. That doesn't exist. And if you take a look at another challenge, it's that audio data is fundamentally very, very difficult to work with. Because the thing is, audio data exists in the natural world. What is audio? It's vibrations of air molecules. And vibrations of air molecules are fast. And audio is recorded at over, say, 44 kilohertz. That's a lot of data. 44,000 data points every single second. There are usually only 44,000 data points in an individual low-resolution image. So, of course, there are lots of challenges to work around when it comes to audio. But companies like IBM, Google, Microsoft have actually worked around these challenges, and they're working towards creating different services to make it easier for developers. So again, on a very, very high level, there's natural language understanding, there's computer vision, there's audio data, and of course there's the traditional set of tabular data understanding, which is essentially structured data understanding.
Some of the most common application areas of AI include natural language processing, speech, and computer vision. Now, let's look at each of these in turn. Humans have the most advanced method of communication, which is known as natural language. While humans can use computers to send voice and text messages to each other, computers do not innately know how to process natural language. Natural language processing is a subset of artificial intelligence that enables computers to understand the meaning of human language. Natural language processing uses machine learning and deep learning algorithms to discern a word's semantic meaning. It does this by deconstructing sentences grammatically, relationally, and structurally, and understanding the context of use. For instance, based on the context of a conversation, NLP can determine if the word cloud is a reference to cloud computing or the massive condensed water vapor floating in the sky. NLP systems might also be able to understand intent and emotion, such as whether you are asking a question out of frustration, confusion, or irritation. Understanding the real intent of the user's language, NLP systems draw inferences through a broad array of linguistic models and algorithms. Natural language processing is broken down into many subcategories related to audio and visual tasks. For computers to communicate in natural language, they need to be able to convert speech into text, so communication is more natural and easy to process. They also need to be able to convert text to speech, so users can interact with computers without the requirement to stare at a screen. The older iterations of speech-to-text technology required programmers to go through a tedious process of discovering and codifying the rules of classifying and converting voice samples into text. With neural networks, instead of coding the rules, you provide voice samples and their corresponding text. The neural network finds the common patterns among the pronunciation of words and then learns to map new voice recordings to their corresponding texts. These advances in speech-to-text technology are the reason we have real-time transcription. Google uses AI-powered speech-to-text in their call screen feature to handle scam calls and show you the text of the person speaking in real time. YouTube uses this to provide automated closed captioning. The flip side of speech-to-text is text-to-speech, also known as speech synthesis. In the past, the creation of a voice model required hundreds of hours of coding. Now, with the help of neural networks, synthesizing human voice has become possible. First, a neural network ingests numerous samples of a person's voice until it can tell whether a new voice sample belongs to the same person. Then, a second neural network generates audio data and runs it through the first network to see if it validates it as belonging to the subject. If it does not, the generator corrects its sample and reruns it through the classifier. The two networks repeat the process until they generate samples that sound natural. Companies use AI-powered voice synthesis to enhance customer experience and give their brands their unique voice. In the medical field, this technology is helping ALS patients regain their true voice instead of using a computerized voice. The field of computer vision focuses on replicating parts of the complexity of the human visual system and enabling computers to identify and process objects in images and videos in the same way humans do. Computer vision is one of the technologies that enables the digital world to interact with the physical world. The field of computer vision has taken great leaps in recent years and surpasses humans in tasks related to detecting and labeling objects, thanks to advances in deep learning and neural networks. This technology enables self-driving cars to make sense of their surroundings. It plays a vital role in facial recognition applications, allowing computers to match images of people's faces to their identities. It also plays a crucial role in augmented and mixed reality, the technology that allows computing devices, such as smartphones, tablets, and smart glasses, to overlay and embed virtual objects on real-world imagery. Online photo libraries like Google Photos use computer vision to detect objects and classify images by the type of content they contain.
Can you tell us a little bit about the work you're doing with self-driving cars?
I've been working on self-driving cars for the last few years. It's a domain that's exploded, obviously, in interest since early competitions back in the 2005 domain. And what we've been working on really is putting together our own self-driving vehicle that was able to drive on public roads in the region of Waterloo last August. With the self-driving cars area, one of our key research domains is in 3D object detection. So this remains a challenging task for algorithms to perform automatically, trying to identify every vehicle, every pedestrian, every sign that's in a driving environment so that the vehicle can make the correct decisions about how it should move and interact with those vehicles. And so we work extensively on how we take in laser data and vision data and radar data and then fuse that into a complete view of the world around the vehicle.
When we think of computer vision, we usually think immediately of self-driving cars. And why is that? Well, it's because it's hard to pay attention when driving on the road, right? You can't both be looking at your smartphone and also be looking at the road at the same time. Of course, it's sometimes hard to predict what people are going to be doing on the street as well when they're crossing the street. with their bike or skateboard or whatnot. So it's great when we have some sort of camera or sensor that can help us detect these things and prevent accidents before they could potentially occur. And that's one of the limitations of human vision is attention, is visual attention. So I could be looking at you, Rav, but behind you could be this delicious slice of pizza. But I can only pay attention to one or just some limited number of things at a time. But I can't attend to everything in my visual field all at once at the same time, like a camera could, or like how computer vision could potentially do so. And so that's one of the great things that cameras and computer vision is good for, helping us pay attention to the whole world around us without having us to look around and make sure that we're paying attention to everything. And that's just in self-driving cars. So I think we all kind of have a good sense of how that shapes, how AI and computer vision shapes the driving and transportation industry.
Well, self-driving cars are certainly the future, and there's tremendous interest right now in self-driving vehicles, in part because of their potential to really change the way our society works and operates. I'm very excited about being able to get into a self-driving car and read or sit on the phone on the way to work instead of having to pilot through Toronto traffic. So I think they represent a really exciting step forward, but there's still lots to do. We still have lots of interesting challenges to solve in the self-driving space before we have really robust and safe cars that are able to drive themselves 100% of the time autonomously on our roads.
We've just launched our own self-driving car specialization on Coursera, and we'd be really happy to see students in this specialization also come and learn more about self-driving. It's a wonderful starting point. It gives you a really nice perspective on the different components of the self-driving software stack and how it actually works. So everywhere from how it perceives the environment, how it makes decisions and plans its way through that environment, to how it controls the vehicle and makes sure it executes those plans safely. So you'll get a nice broad sweep of all of those things from that specialization. And from there, you then want to become really good and really deep in one particular area if you want to work in this domain. Because again, there's so many layers behind this. There's so much foundational knowledge you need to start contributing that you can't go wrong. If you find something interesting, just go after it. And I'm sure there'll be companies that will need you for this.